Okay, today I'm off in a completely different direction. We've pretty much finished 3JS unless I come up with some other stuff I want to show you. But for the time being, I'm going to move on into chapter 10 of our author's book. Let me get a share screen going here. Okay, so what we're talking about in chapter 10 are procedural methods. One way of dealing with objects in our synthetic world is by explicitly defining how and when things move. And this is basically what the trackball and flyover interfaces do. Neither the trackball nor our little airplane are physics-based devices. But another approach to animating things in the world is to use physics-based modeling. We're going to model the physics, and then we'll use those results to drive the animation, the graphics. One style of physics-based modeling uses particle systems, collections of point masses whose behavior is controlled by differential equations. I'll show you some examples of these. Instead of modeling a deformable object, we would model a collection of 3D points connected by springs. With our convex material, we could actually wrap this object in a surface and have it behave physically somehow. There are a lot of applications: fluid mechanics, flocking behaviors, n-body problems, any number of applications. We're going to consider a special case, the Newtonian particles. And by a Newtonian particle, it's going to obey Newton's law, F equals ma. Those of you who took physics have probably seen that. Our particles are considered to be a point mass, so they have no size. We can build bigger objects out of collections of points, but for the time being, a particle consists of a point. It has a mass to appear in Newton's equation, the m there. And we have 6 degrees of freedom. The degrees of freedom are the x, y, and z position coordinates and the components of velocity in x, y, and z, where it is and how fast it's going. And we'll see as we go along here why we need to know where it is and how fast it's going. Some background on Newton's law. He published it in 1687 in the Principia, where he also defined calculus that troubles us to this day. Newton's first law was stolen directly from Galileo. Galileo observed that in the absence of unbalanced forces, an object remains at rest or moves in a straight line at a constant velocity, a remarkable observation given that we live in a world dominated by friction. So Newton's second law was that the time rate of change of momentum is proportional to the force. This was from the observation that if you pushed something that was light, didn't weigh much, it would then move fast. And if you pushed something heavy, with the same amount of push, it moved slow. Light and heavy correspond to mass, and Newton defined momentum to be the product of mass and velocity, light and heavy times fast and slow. And his second law was rate of change of the quantity mass times velocity was equal to the force. And this also defined what he meant by force, this equation. For those of you interested in the physics things here, mass is a parameter that expresses the proportionality between the rate of change of momentum and the force. And as a parameter, we often measure it by fitting a theory to observational data. This is how balance scales work and spring-based scales and everything. They're a model. We observe the displacement of it, and from that we measure the mass. Newton's second law also is an example of a conservation law, in that the rate of change of momentum, mv, is equal to the force. mv is the conserved quantity, and force is the source of momentum. And so if there's no source, no unbalanced force, then the rate of change of momentum is zero. Momentum doesn't change, it's conserved. This is all physics stuff. So it's also a vector equation. We have components in the x, y, and z, or whatever Cartesian, whatever coordinate system we use, but we're going to use Cartesian in the x, y, and z. And so we can write this as a vector equation by putting little hats over the v and the f that indicate that they're vectors with three components in the Cartesian coordinate system. When we talk about speed, that's the magnitude of the velocity vector. So that's the square root of vx squared plus vy squared plus v squared. And since m is inside the derivative here, I'm going to make a simplifying assumption that when I take that derivative of the product, which usually gives me two terms, an m dv dt and a v dm dt, I'm going to assume that the mass is not changing, so I can throw away that term. I don't have to deal with rate of change of mass. If you're doing rockets whose masses change profoundly as they use up their fuel, you have to include that term. So when we talk about the rate of change of velocity, that's what we call the acceleration. And when we talk about the rate of change of position, that's what we call the velocity. And so each of our little vector equations, dx dt is vx, dy dt is vy, and dz dt is vz. And so our f equals m dv dt is ma. I'm talking about just the x component here. And that's now the second derivative of x with respect to t. So in our solutions here, we're dealing with second order differential equations. And F equals ma, that you're all familiar with from your physics class, is a special case of Newton's second law, where mass is constant. So we don't solve this second order equation directly. Instead, we solve it by solving the set of coupled first order equations. Force is mass times acceleration, rate of change of velocity. Velocity is rate of change of position. So we have two first order coupled equations that we can solve for our F equals ma. I'll do an analytic solution here quickly. Uniform gravity, the acceleration of gravity is negative 9.8 meters per second. That means that at time 0, we start at v0. At 1 second, we're moving 9.8. At 2 seconds, we're moving 19.6, etc. The velocity increases with this rate. So going through the integrals, if I solve for dv dt in here, it's g. I can integrate both sides from an initial velocity to a velocity at some time, and g from 0 to t. I get v0, v of t minus v0 is gt, or the velocity as a function of time is its initial velocity plus the acceleration times time. I need that initial velocity, v0, as a constant of integration. Doing the next step, I solve for dx dt is v0 plus gt. I integrate from an initial position to a position at some time, 0 to t, v0 plus gt squared, gt. Integrating that, I get x of t is x0 plus v0t plus 1/2 gt squared. This turns out to be a parabola in t. And notice again, I need this initial position, x0, a constant of integration. This is why I have 6 degrees of freedom. I need to know where it is, the x's, and I need to know how fast it's going, the v's, in order to predict where it will be and how fast it will be going at some later time. If g happened to depend on time, I can't do this integral, and so this all breaks down. So we have numerical methods. A generic first order equation is rate of change of something is equal to some function of that something and perhaps time. From the definition of the derivative, I have that the definition is y at t plus delta t minus y at t over delta t. In the limit as delta t gets infinitely small, this is the definition of the derivative. This is equal to this function at y and t. And if I drop this limit and just take y at t plus delta t as y at the n plus 1th time step and y at t as the y at the nth time step, then I have a finite difference approximation where the difference between these two solutions over delta t is equal to my function evaluated at the beginning here at y of n and at t of n at time t. So if I solve this for ym plus 1, I have now a recursion relationship where given its position at any time and the evaluation of this function g at that value of y and that value of t, I can step forward to another value at some later time step with this simple recursion formula. And this is called Euler's method. Basically, we're taking the slope, that's what the g is the slope of the curve here, and we're extrapolating forward in time using that slope. And you can see, of course, that it's not exact. It's a numerical method. Now, with Newton's law, we have two coupled first order equations. dx dt is v and dv dt is f over m. And this f over m is what we have to evaluate, how the force depends on position, velocity, and time. But we have two recursion relationships. We have one for x that goes with v delta t, and we have one that v that goes with g delta t. And notice everything on the right-hand side is evaluated at the nth step and used to project forward into the n plus 1th step. So a simple code fragment here. We have some loop. We're replacing in place. So xn is just incremented by vn delta t, and vn is just incremented by whatever this function is, evaluated at x, v, and t times delta t, and we go around that loop, and that's called the Euler method. If we exchange the order here so that we calculate the v first, and then use that new updated v to update x, we have an improved method that is more stable. It's stable because it's a two-point method. It uses information at the beginning and at the end of the interval, and this is called Euler Cromer. Now, in any of these methods, the hard part is defining that g function, the acceleration, how it depends on position, velocity, and time. With independent particles that are not interacting with respect to each other, but are just responding to gravity or wind blowing on them, the complexity is order n. The calculation scales is the number of particles. If we have coupled particles, then how that complexity is going to depend on how these particles are connected. If we had some mesh of materials that were connected only to their neighbors, like a mesh with springs connecting things, then the problem still scales as order n. But if we get into the attractive or repulsive forces, such as the inverse square gravity or electrostatic forces, Then the complexity scales as order n squared, since for each particle, we have to calculate the force exerted on it by each other particle. So we have to go through each particle, go through all the others to calculate the force on it. And so it's an order n squared. That's the so-called n-body problem. So a schematic of how we might set this up. We'll have position, velocity, and force. We have some initial state that sets position and velocity. We have to define where things are and how fast they're going. Then we have some time step that evaluates the force at that position, velocity of time. We have some numerical method that takes that force, position, and velocity and updates it with a delta time, and then we're going to render it. And so this is the schematic of how we might set things up. Now, independent particles, that force only depends on position, velocity, and time as it responds to external forces. With uniform gravity, the force is mg. We could express this as a vector with a minus g in the y component. And if we had wind, it might vary sinusoidally or some other dependence on time. With our little bouncing ball, we slowed down the particles bouncing to kind of model friction by reducing the velocity by some fraction. But a better way is to do this by recognizing that viscous drag is proportional to the velocity squared. So here's our viscous drag that's proportional to the velocity squared. It's in the direction of the velocity. So here's a unit vector in the direction of the velocity, and it retards that motion. So it's a minus sign. So we can do that with a dot product and a square root. With a checkerboard mesh of particles that are connected to each other, we have only its nearest neighbors. So we might have it connected to the up, the down, the left, and the right particles. We'd have to deal with particles that don't have full neighbors. The edges only have 3 because they don't have one to the left. And the corners only have 2 because they don't have one to the up and to the left. And so we have to have special rules for them. And complexity is order n squared. This is the kind of setup we might have for one of these meshes where particle ij is connected to its 4 neighbors by some spring whose displacement is the difference between the positions p and q. And we could then form a spring that has some rest length s. And so the difference between d and s is going to be whether the spring is compressed and it's pushing out, or whether the spring is extended and it's pulling in. And so we can have that force applied in equal and opposite ways to particle Q and particle P. Spring without damping will oscillate forever. We can do this little trick, or we can use the more physically correct velocity squared damping. With inverse square, the inverse square, also from Newton, says that the magnitude of the gravitational force between 2 objects is inversely proportional to the square of the distance. So here's the magnitude of the force. There's some constant of proportionality. It has to do with the masses divided by their separations squared. It's directed along a vector connecting the objects. So here's the unit vector that connects these 2 objects. The d is the vector between them. D over magnitude d is a unit vector, and it has a sign that is negative for attraction. It pulls. That would be a plus for repulsion. It pushes. And we often combine these 2 terms into a magnitude d cubed. So even though we're doing an inverse square law here, we end up with a distance cubed. But the reason for that is that this is now a unit vector. There are other inverse N laws that model shorter range forces. We might use them for collisions. So here are inverse N laws. This is inverse square that falls off kind of slowly, but as N gets larger, it falls off more quickly. And so we can use a repulsive force like an N equal 8 that would be very, very weak out here, but when you got in close would suddenly get very hard to push away. And so this is one way of modeling collisions between particles. This is often done in molecular modeling, where we combine in what's called the Lennard-Jones potential an attractive inverse 7th, that's this one, with a repulsive inverse 12th or inverse 13th that pushes our molecules away from each other. This is what Lennard-Jones looks like. This is the potential that's a combination of the inverse 6 and the inverse 13th. This is our potential for Lennard-Jones. So with an n-body problem, you've got to calculate these forces on each particle due to every other particle. This is why it's order n squared. In some cases, you can neglect particles that are far away, because as you saw back here, the forces fall off pretty quickly with distance. One approach is to sort them by distance and then only include the force of the m nearest ones. Since sorting is n log n, if m, the number that you're going to use, is less than log of n, the total number of particles, then sorting all your particles by distance and only using the m closest is one approach. Another is to put all the particles in different boxes, update which box a particle belongs to, and only calculate the forces between the particles in your box and its surrounding boxes. So that eliminates a lot of the far away particles. A particle constructor here, we might have color, position, velocity, and mass. This would be a constructor for particles. And so we would go through our setup, push these into particles, particle mass, particle color, go through each of the x, y, and z coordinates of our particle and define a position, here random, and a velocity, here random, and then push those coordinates, those particles and their colors into the different arrays that we would send to the GPU. This is following our author's way of doing this. It's a bit more, it's possible to do in 3JS as well. Just a rough draft of particles in a box, particle coordinates, forces, dealing with collisions. This is our numerical method, incidentally. We have delta P is the velocity that we're scaling a vector particle velocity by dt. We add that to the particle position. We scale the forces by the particle mass, dt over particle mass, and we add that to the velocity. So there's our numerical method. We might have to check for collisions. I'm doing this in the CPU rather than the GPU, so I have to update the coordinate positions here, calculating our trajectories with Euler steps. And as I mentioned, a way to do collisions is repulsive forces, short range, high exponent, inverse d to the n forces. But you can also check for penetration of the surface and then calculate where the particle would have ended up had it experienced an elastic or partially elastic collision. In an elastic collision, the normal component of the velocity reverses. The velocity in gets turned around into a velocity out, while the tangential component is unchanged. Note this is how light reflects to form a perfectly specular surface. The angle of incidence is equal to the angle of reflection. In a partially elastic collision, the normal component, in addition to being reversed, is also reduced in magnitude by a fraction known as the coefficient of restitution. And basically what this means is if you have a coefficient of restitution of 0.5, when it bounces half as high each time. So the bounce runs down as it bounces. This is a little schematic. If we detect a collision here, and we have full elasticity in that same time, it would have ended up here. So we reverse the velocity, leave the tangential velocity alone, and put the particle the same distance in front of the barrier that we found it behind the barrier. And if we have a coefficient of restitution of 0.5, the velocity is a half, so it only moves out half as far. Tangential component is left alone. And so this is how we would handle this. Here's a code fragment for doing this for a particle moving in the plus x direction with a flat wall at L equal x, updating the positions, reversing the velocity, and putting it out here some distance based on this coefficient of restitution. Collisions with arbitrary shapes are much, much harder. In 415, I do collisions with spheres. Unity doesn't let you collide with arbitrary meshes because it's too hard, so they make you use a convex shrink wrap as your shape. That's a little bit easier, but that's the kind of stuff. I'm going to stop here. I'm going to stop here because I think I've gone far enough for a single lecture. So let me stop sharing. I will pick up with the rest of this and show you this example the next time. So I'm going to stop sharing. I'm going to end the video. So I'll see you. This is for Friday, April 10th. And so I'll see you on Monday. Stop recording. Bye.